This is a picture of the Bohr model of the atom. It will help you very much when you try to understand why the flame tests change the color of the flame. This model of the atom has the center of the atom as a positively charged nucleus, and the outside of the atom as some negatively charged electron. There could be more than one electron outside here, and there could be more than one particle in the nucleus inside here. This is just one model to help us to understand the atom. A model in chemistry is an explanation or some representation. It is never complete. It is never perfect. For example, this model of the atom is woefully inaccurate, and there is evidence that it is woefully inaccurate in other experiments. However, it is good enough for the flame test experiment that you did. So let me go on here. Now, here you could see more than one path for that blue electron. It happens to be the case in this model of the atom that when the electron has higher energy, it is able to jump to paths around the nucleus that are farther from the nucleus. So this is very important. Close to the nucleus, the electron has lower energy. Far from the nucleus, the electron has higher energy. That one electron in this hydrogen atom is able to jump from path to path. It could jump to higher paths if it absorbs energy, and it could jump to lower paths if it releases some energy. These paths are called energy levels. Energy levels. The hydrogen atom, all hydrogen atoms in the universe have the same energy levels. They all have a certain energy for that first level. First level is called the ground state. There is a certain energy for that second level, a certain energy for that third level. The amounts of energies that each level represents is a fingerprint for that element. All hydrogen atoms have the same energy fingerprint. Now again, what I mean by fingerprint is the set of exact energies that each of these levels represent. All calcium atoms have a fingerprint that is completely different from the hydrogen atom's fingerprint. All strontium atoms have a fingerprint that is completely different from the hydrogen atom's fingerprint or the calcium atom's fingerprint. Now, in order for an electron to travel to a higher energy level within its atom's energy fingerprint, it has to absorb energy. And this is how it happens. Some energy hits that electron, and when it absorbs that specific amount of energy, it can jump to one higher level. If the amount of energy is just right, it could jump one energy level, or if it's just right, it could jump two energy levels. It could jump any number of energy levels. But each time, that energy has to be just right, a certain quantity of energy. We call that quantity a quantum. So this is why this type of chemistry, that's flame test and these sorts of things, is called quantum chemistry, because the energy that the electron absorbs is always a certain set quantity. Now, that quantity depends on the exact energies of each level. So the quantity to jump from level 2 to level 3, let's say, will be the same for all hydrogen atoms, but it will be different between hydrogen and calcium. And it will be different again for sodium. It will be different again for strontium. So these quanta of energy, the plural for quantum is quanta. So these quanta of energy are all different for different elements. Okay, now why does that change the color of the flame? Well, it's important for you to know that when you heated up your wooden stick with the solution soaked into the tip, when you heated that up in the flame, that flame was giving to the atoms in the solution that you soaked up in the stick, it was giving to those atoms all kinds of different quanta of energy, just random bombardment with different quantities of energy. So with all that random bombardment of energy quanta, it was very likely that the electrons in the solution that you soaked on the tip of that wooden stick, it was very likely that those electrons could find the quantum that they needed to jump one energy level up or two energy levels up, something like that. So that's what they did. They absorbed the correct quanta of energy and they jumped up a couple of energy levels, one or a couple of energy levels. Did that create the colored flame? No, not yet, because the colored flame does not represent an absorption of energy, it represents an emission of energy. Remember, I turned off the lights. When I turned off the lights, you were able to see the colored flame. That means the colored flame was giving light that was going into your eyes. It was not absorbing light, it was giving light. So when does that happen? Here's when it happens. After the electron absorbs a certain quantum or some certain quanta of energy, they go to this higher energy level. But once they're there, they have to come back down to their lower energy levels, because that's what that's what matter does in this universe. When it absorbs energy, it always releases that energy until the entire environment is at the same energy. For example, if you give energy to a ball of metal by putting it in the oven, now it is hot. You put that ball of metal on the table. It will release its energy until it has the same temperature as everything in the room, right? If you take a piece of ice from the freezer and then you put it on the table, it will absorb energy from the room until that water in that ice is the same temperature as everything in the room. So this equilibrium, the same, having the same energy as the environment, this equilibrium is kind of a balance that all matter does in this universe. And when you die, your body will do the same thing. It will cool off until it is the same temperature as everything else around it. So, sorry, that was kind of morbid, right? Now, watch what happens after these electrons in these higher energy levels come back down to their lower energy levels. Did you see that? Here. So this electron goes up because it absorbs a quantum of energy, and then it goes down. And when it goes down, did you see that? When it goes down, it releases that same quantum of energy. That's right, it releases that quantum of energy, and when it does that, it releases it as light. So that's what you saw. You saw the electrons, after they absorbed the energy. It was not easy to observe the absorption of energy. In fact, it was impossible to observe the absorption of energy. However, after they did that, when they relaxed down to a lower energy level, they released a certain quantum of energy, and that was the color that you saw. For the strontium, it was red. Does that mean all of the energy that got released from your wooden stick soaked in the strontium chloride solution was what was red? No. It doesn't mean that it was all red. It just means that all of the different colors of light that were getting released by that strontium add up to that certain shade of red for that strontium. Here, let me show you in a little more detail. There is a rainbow picture here at some point. Yes. Do you remember that white cylinder tube that I had you look at the lights with? Through that tube, you saw this rainbow spectrum from the lights of the room, didn't you? This it didn't quite work with the flames because the flames were too, I guess, flickery. But if you were to point the slit of that white cylinder at the flames exactly, and if you were to observe on this in your peripheral vision as you look through that tube, you would have seen certain thin bands of color. Instead of seeing a continuous rainbow band, you would have seen certain thin bands of color. It would have been just the same height as the rainbow that you saw when you looked at the room lights, except most of this stuff would have been missing. Most of this would have been black, but you would have seen just a tiny band, a very thin band of a very specific shade of purple, let's say, or a very specific shade of dark blue, a very specific shade of light blue, a very specific shade of red. So every compound that you observe the flame test for would give a flame that would give a different spectrum, a different set of very specific shades of colors. That set is the fingerprint for that compound. So every little band here, every thin band of color represents one transition of an electron from one energy level down to a lower energy level. The transition from this third energy level to this second energy level, level 3 to level 2. That transition in this case is shown as this orange-red color, also known as vermilion. The transition from the fourth energy level down to the second energy level, here it is shown as this light blue color. You see, when the electron jumps from level 4 to level 2, it must release a quantum of energy. And that quantum of energy is released as a certain color of light. You could see here that the energy difference here between level 3 and level 2 is short. The energy difference between level, let's see, this is 3, 4, 5, 6, between level 6 and level 2 is long, is great. So a short energy hop is a small amount of energy. A long energy hop is a large amount of energy. Notice that purple represents a larger amount of energy than red, and that is true. We'll learn later through some video that I will assign to you as homework in another week. We'll learn later that the red color is a low energy color compared to purple. In fact, the order of colors on any natural rainbow is an order of energy. Red is lower energy, yellow is higher energy, green is higher energy, blue is higher energy, and violet. Violet is the highest energy. It's important to understand that this is violet. It's important to call this violet rather than purple. Now, of course, beyond violet, there is even higher energy, and you know that as ultraviolet. And below red, there is also even lower energy, and you know that as infrared. So this is the reason why you saw the characteristic colors that the flame tests revealed. Okay, let me just. That was very complicated, and I want to make sure that you understand this by reviewing this briefly. Right? So, to review, the one model of the atom says that there is a nucleus in the middle and there's an electron that goes around it. And that electron can exist at different energies. Higher energies are farther from the middle, the nucleus, and lower energies are closer to the middle. Now the electron can travel between energy levels simply by absorbing a certain quantum of energy. Each energy level for any particular element has the exact same amount of energy. So to get from level 2 to level 3, all hydrogen atoms need this amount of energy. To get from level 2 to level 3 for a calcium atom, it is a different amount of energy. These energy amounts are characteristic for each element. They're like a fingerprint for the element. Now, we can't see any of this. However, when the electron relaxes, when it loses energy, when it releases energy to the environment, we do see that. And you saw that in the flame tests. Here you Here you see an electron releasing energy. That energy that just got released, that is released in the form of light. It is always the same exact color of light. It is because each color is a certain quantity of energy, a quantum of energy. So when that gets released, you see that as the glowing color in the flame. Now, every transition from a higher energy level to a lower energy level gives a certain color of light, a certain quantum of energy, and that color of light is visible through one of those white tubes that you used as a very thin band. You saw this very broad band by looking at the room lights because they are designed to give white light. However, when you look at the flame color given by a certain compound through one of these flame tests, you would only see very thin bands of certain colors. And when you combine all of those colors, all of those exact shades of different colors, you get the resultant color of the flame. For strontium, it was that red, crimson flame. For potassium, remember, it was that lilac, that pretty purple color. And then for sodium, remember, it was the orange color. And then for calcium, I think only the people around Emily were able to get the calcium to work, but the calcium gives this orange, red, or vermilion color. I think Emily aptly named this as fuchsia. Yes, that is a good description. So the fuchsia would have been the average of all of the very specific shades of different colors. That there would have only been three or four of very thin bands if you were to look at that calcium flame through the white tube, which is called a spectroscope, by the way. And so that fuchsia color would have been the sum of all of those very thin, very specific shades of different colors. So that is the reason why you saw the flames that you saw. I'll ask you for your homework to do the flame test again, just very briefly, just very quickly, online in a simulation. All right? Thank you.